Good morning, Dylan. How are you? I'm good, thanks. Can you hear me well? All good? Okay, I think we can now start. So today we will be looking at second topic of shallow footing design, which is design of shallow footing based on soil reactivity. Okay. Last week we talked about design of shallow footing based on bearing strength or bearing capacity. This week we are starting our first topic with design of shallow footing based on soil reactivity, which in the problematic soils. Okay, so let's start first talking about what is the soil reactivity and in which soil this problem appears. So we have the expansive soil. So the soil reactivity occurs in the expansive soil or swelling soils. What is the problem with the swelling soil or expansive soil? And let's define it. So approximately 30% of all surface soils on Australia are expansive soil. That's why it is very important to understand the behavior of the expansive soil and how to design the shallow footing founded on this soils. The problem with expansive soil is that it shrink and swell due to changes in moisture. So when the water content change, the soil can swell if we have more water content and also shrink if the water content is less or reduced. Okay, so this is an example of the swelling soil or expansive soil. So here, this is the soil normal condition when the moisture content is low. So as you can see, it is very thin and normal. And then when you add water to it or moisture to it, so this soil will and here its volume increase, but filled with air and water. So it become very weak soil. Okay, this is two type of soil and example of the expansive soil. When you add water to this soil, this soil will swell and go up like that above the the container, showing that it has expanded for maybe double size or something like that. Okay, so this is generally the expensive soil, so it is very weak soil, and we cannot found our footing or place our footing on this type of soil. Okay, so any structure located at shallow depths of the ground can be affected by the expansive soils. Because as I mentioned, like if this our ground level, so 30% of Australia has the shallow layer are, I mean, shallow layers means the soil near to the surface are expansive soil. This will affect our structure like pipelines because pipelines are usually constructed at shallow depths. Okay. Also, road pavement because as you know, road pavements are constructed on the ground. And number three is the shallow footing or of lightweight structure. So if you have a residential house like that, so the footing of this house will be constructed on a shallow depths, so it will be affected by the expansive soil. This also pipeline, and this is the root pavement. So that's why we need to be aware of how to deal with the expansive soil. Okay, here is an example of the ground movement of the expansive soil. So if you have a residential or lightweight structure like that, residential building, and we will look at the behavior of the soil underneath this house along the year. So if this is the house here at the construction, so what happened to the soil underneath? So the soil, because it's expansive, so the soil start to swell. So the soil swell around the house because the house also is applying some weight on the soil, so it doesn't move itself. But the soil, like this uh, diagram. So this diagram show how the soil has uh, has expand or has swell due to the moisture. If the moisture increase somewhere here around the house, so this happens. And then after that, after exposed to high temperature, for example, in summer, what happened to the water? The water evaporates or the water content reduced. So the soil becomes dry and it moves like that because the water has moved again out of this area. Okay. Then after 2 or 3 years, what happened when the water increase again? When we add or when we have again some water moisture or some water content, the soil will expand again or swell again. So this keep happening year by year, and we can see here what happened when the soil shrink due to less water content or less water moisture. Okay, so year by year, and after repeating this process, so there is the water become the soil layer become like that. So expand and dry, expand and dry, expand and shrink. So there is applied uplift pressure to our structure. So we have uplift on the structures, which will cause cracks and damage of the structure. Okay, so this happen after applying or after the process of swelling and drying all the time. Then again, when we have water, this when the water go out, and this when the water get in again. So the water, the soil surface, as you can see, expanded all this all expand, and also not an even surface, some not an even or not even surface. Okay, so this is like brief explanation of what happened, the process of swelling and shrinkage of the expansive soil. Okay, do you have any question, guys? Okay, now if you have any questions, just let me know. And also, do you have any problem with the slide? All good, and the voice? Can you hear me clearly? Okay, thank you, guys. Okay, now we shift to the important part of our lecture, which is the design based on soil reactivity for expansive soil. The standard related to the design of shallow foundation is AS 2870 2011, which is the standard for footing design. We have used this one in last lecture. Okay, here in this section, and in this standard, section 3 is related to normal site based on YS characteristic of soil movement. So section 3 of the standard will be dealing with the normal sites of expansive soil. So some expansive soil are not that problematic. So section 3 of the standard will be dealing with that based on a parameter called YS, which is the characteristics of soil movement. Okay, section 4 will be dealing with the section designed by engineering principle for B site. So we'll be dealing with the problematic sites of expansive soil based on engineering principle. Okay, in our course, we are only focusing on section 3. okay, which is for normal sites and expansive soil behavior based on the soil movement YS. Okay, we have also another appendix or section in the standard, appendix H and CH for design for trees. Because as you know, the existence of trees affects the footing design. So there is appendix C, H, and H for the trees. Okay, let's start with section 3 of the standard for footing for soil activity. And let's see what is the footing options we have for expansive soil in normal sites. So the first one is stiffened raft. Second one is footing slab. The third is waffle raft. The fourth is stiffened slab with deep edge beam. The fifth is strip footing. So all this type of footing can be used for the expansive soil in normal sites. Let's see, let's have a look what are these options. So this is the first option, this is the stiffened raft, sorry. So the stiffened raft, this is a cross section of the raft. So the raft has slab, mainly slab. Slab means, as you know, this is slab. So it is a wide concrete area and it has some reinforcement in both direction. As you can see, here is the reinforcement in X direction and the other like small circles indicates the reinforcement in the other direction or in the perpendicular direction. And we have this slab is stiffened with some drop beams like that. So if you can see that. Okay, so we have stiffened drafts. In this stiffened or small beams, we have also some rail. We don't have stirrups, so just remove the stirrups. Okay, so in this stiffened or small beams, we have reinforcement here. So this is the reinforcement of the stiffeners or the edge and internal beam. So we call the stiffeners as edge beam and internal beam. So these are shallow beams or small depth beam. So this is the first type of footing we have, stiffened raft. So we have mainly the slab or the raft reinforced with rail in two directions. And then we have beams. We call them edge beams and internal beams, and has also some reinforcement or rail. Okay. And on top of that, you can apply your loads. Okay. Depends on the house or the residential building scenario or design. So as you can see here, here is some walls and here may be some bearing walls or columns. So this is generally the stiffened draft cross section. Another option, another option for the footing options of section 3 is waffle raft. Waffle raft, still a raft, we have also some beams, but in this type we have beams in two directions, not only in one direction. So in this case, we have something like that. So is this our cross section? So we have beams in both directions. So the difference between stiffened raft and waffle raft is the waffle raft has beams in both directions. But in the previous type, which is the stiffened raft, we have beams only in one direction. So the waffle raft is uh, is quite close to the stiffened raft, but we have beams in two directions or both directions. Another difference is because we have beam in both directions, we are making the spacing between the beams. So if this one beam and this other beam, so the beam spacing, so this beam one, beam two. So we have the beam spacing is a little bit smaller compared to the waffle raft. And again, the design of this raft depends on the scenario of the building and the soil uh, durability or soil strength. Okay, so and the scenario of the building is, for example, we have here clad frame, just example, and we have here bearing wall, and we have on the edge masonry veneer. Okay, so this is, and this one can be used for soil reactivity from low to medium. We will see this later in the lecture. So this can be used for low and medium reactivity soil. So we have looked at these two examples, and the other example can be found in the standard. But let's go through the design procedure or how to select the footing type. So what we need to know to design a footing based on the soil activity. So we need two parameter or two information are needed: the site classification and the superstructure type. So we need to know what is the superstructure and what is the soil. So these two parameters are required for our design. So soil type and structure type. Okay, let's go to know these two information, how to know this information. So if we look here, so what is the site classification is? So the site classification, we have some site classification depend on the soil, and this table gives us the values of YS or the characteristic soil movement. Okay, so this is YS. So we have the first classification is A for most sands and rock sites, and YS is 0 for this type of soil. S is slightly reactive clay sites, YS from 0 to 20 millimeters. M moderately reactive clay or silt, YS from 20 to 40. H1 highly reactive clay sites, from 40 to 60, YS. H2, highly reactive clay sites. So the highly reactive sites are divided to two levels or two classifications from YS from 40 YS from 40 to 60 and YS from 60 to 75. Okay, and if we are on the edge, like for example 40 here and 40 here, you can use either of them. So you can consider it as moderated or highly reactive soil. Here as well, 60 and 60, so you can consider it both, one of both. Okay, so the next one, or the next classification is E for extremely reactive sites. If YS more than 75, so this type is the worst reactive soil behavior. So this very critical one. Okay, and all of those types, the yellow one, and then just highlight them. So this one, all these soils are considered normal sites, normal sites, and can be under section 3. Okay, so the only problematic soil is the E side when Y is more than 75 millimeters. Okay, we have another, so up to here, this is the classification of the soil. So we have another or a second classification, which is the subscript D. So we can have subscript D for semi-arid and arid zone. And we have another classification for B for problem site or problematic site when we have other problems like trees or water reservoir, because as you know, water reservoir also has a high amount of water, so it will affect the soil movement. Okay, so this is our soil or site classification or soil classification based on the behavior of soil, and the standard give us the characteristic soil movement for each type of soil. This means how much the soil will expand in the normal condition or when we add the water, sorry, when we add the water content. So YS means the movement of the soil when we add water content or when we reduce the water content when it shrinks. So this is the maximum movement can happen when it is wet or when it is dry. Okay. In this slide, we will be looking at how YS is calculated. So the characteristic soil movement. So YS is the summation of IBT times delta U times H. This is a simplified form, oftenly done in the sublayer of the soil. So IBT is a soil parameter. okay, which indicate how much the soil move per unit change of suction. This is the definition of this parameter. You just need to know this information like for knowledge, and we are not very looking deep in this one. So, but just to have idea about how they calculate this one, and I will show you how we will need this in the examples and in the final exam. Okay, so just know how they calculate YS. Delta U is the suction change between summer and winter. So as you know, the suction or the water movement out of the soil and into the soil change between the seasons, summer and winter, because summer is dry season, winter is wet season. H is the depth of suction change. Okay, so these are the three parameters used to calculate Y. Okay, let's define first the suction. So the suction here, for example, if we have a layer of soil and we have some soil particles, for example, like that. Okay, and in between the soil, we have some water. Okay, so when suction happens, what happened to the water? The water try to push the water try to push the soil particles to get out of the soil. Okay, so what happened to the soil layer when the water moves out? So also the soil will become very closer. The soil particles will become closer, and the soil shrink. So this is how the soil shrink due to suction, and the water will push the soil particle while moving out of the soil. So this is what we are looking at, the suction and what the suction happens on the soil particle. Okay, so this is what we are looking at for suction, and now we can just have some guideline about the values. Again, what is YS? YS is summation IBT times delta U times HS. So in this slide, we will have some general guidelines of the parameter delta U and HS. Okay, so the standard give us the value of delta U and HS in some regions of Australia. So we have in Adelaide, in Melbourne East and Melbourne West and Wodonga. As you can see, delta U has a similar value in most areas of Australia, which is 1.2 BF. Okay, and BF is a unit called picofarad to measure the ability of soil sorry, to measure the ability of the system to store an electrical charge. So it is electrical unit. We don't worry too much about the unit, but just for your information. So we have delta U 1.2 picofarad, and we have HS in meter. HS in Adelaide is 4 meter. In Melbourne West from 2.3 to 3. In East 1.5, and in Albury Wodonga is 3. Okay, and the formula to find the suction delta U in picofarad equal to log suction in kPa plus 1.1. We also don't worry about this formula, but let's look at how the value of delta U change, or how they calculate delta U. So if we look at this diagram, this is the delta U diagram in the summer or dry ground. So this is the value of delta U in the summer. Okay. So, and in the wet ground condition in water and spring, what happened to this delta U? Delta U takes the curve, the blue curve, instead of the, so I will just use a different color. So delta U, because the water become wet, so we have another movement in this direction, so this become delta U. And what is the depth of change of delta U, or the suction? Delta HS, or the HS. So this is the original curve. This is the original curve in summer or dry, and this is the curve in winter. So the difference between the two curves is delta U, and the depth of change of the curve is HS. So HS in Adelaide is 4 meter, and delta U in Adelaide is 1.2 meter. Sorry, is 1.2 picofarad. Okay, so now we know some information about delta U and HS. Now, how can we find IBT? IBT is measured in the lab, soil lab. So you can find it using suction measurement, and there is a video to watch it. And core shrinkage test, there is also a video, and swelling test, and all the data from this three tests can be interpreted to get IBT. Okay, for example, this is the core shrinkage test. We extract a core from soil and then measure the shrinkage of this core, because as you know, when the soil is dry, what happened to, like, for example, if this is the soil, when it is dry, so the volume of it will be less, so you have another measurement. So if this L1, L2, so the difference will be delta, or the shrinkage, and this delta can be interpreted to IBT. Okay, and you can watch the three videos to have an idea about this test. Okay, now we finalize the first, as I will go back for few slides. So what was the information needed to design footing on the expensive soil? We need two information. Site classification already finished, so the second is superstructure type. So if we go forward to the slide, so this is the type of structure and deflection limit based on the standard AS 2870. Okay, so this is are the structure types of superstructure that can be used on the expansive soil or the commonly used in expansive soil here in Australia. And the standard give us the type of structure, like for example, clad frame (CF), articulated masonry veneer (AMV), masonry veneer (MV), articulated full masonry (AFM), and full masonry (FM). The max deflection movement of the footing underneath this type of structure should be less than L over 300, L over 400 for articulated masonry, L over 600 for masonry veneer, and L over 800 for full masonry, articulated full masonry, and L over 2000 for full masonry. And the maximum difference movement should be this value 40 millimeter, 30 millimeter, 20 millimeter for each type of superstructure. Okay, these limits are very important to our design, our footing design, because it can change or alternate the building type because of the soil. If the soil is not satisfying this condition, so I need to change the superstructure type to fit with the requirement of the standard. Okay, here is the types of structure and the deflection limit given in the diagram instead of table. So these are the clad frame construction, CF construction. Again, the max difference of movement should be L over 300 and less than 40 millimeters. And for brick masonry veneer, and this is the cross section of the brick masonry veneer, should be L over 600 and less than 20 millimeters. So the maximum movement below shouldn't be more than 20 millimeters. Here shouldn't be more than 40 millimeters. And for the articulated brick construction, the maximum movement L over 800 and should be less than 15 millimeters. And the full masonry should be L over 2000 and less than 10 millimeters. Okay. So these are the types of structure we have, and we will deal with them in our course. So now we jump to the design steps of shallow footing based on soil reactivity. What are the steps of design? First, we need to decide the site classification, YS, and the area of construction. So we need to know the soil classification or the site classification to know what is YS. Then we need to, based on YS, we need to decide the footing type from stiffened raft or waffle raft and so on. Number 3 is to find the appropriate chart from section 3. Number 4 is to read the necessary information from the chart. So using the first two, we will go to section 3 to find some information that will help us to complete the design. Then draw a section elevation of the footing you have selected. Okay, this map give us the soil reactivity map of location of Adelaide. Locations in Adelaide. So you can have a look on this map. So when you design a building somewhere, you go to this map to find how much the YS or how much the soil reactivity level of this site. Okay. So now we will have an example on Stephen draft section, and here is a Stephen draft, and you don't have to memorize this cross section because it is given in the Australian Standard 2870 2011. So you can go to the standard uh, to get this cross section details. And here is the table. So for example, if we are already selecting a Stephen draft for a site, then we go to the table of the Australian standard AS 2870. So we need to know the site class and we need to know the type of construction. So this two information as we mentioned. So for example, just an example, if we have in this example a class A site and a clad frame superstructure. So we already know these two information. And now we need to find the values we required from here. So for the Stephen draft, the depth D is 300. So if we go to know what is D, D is the depth of the beams. So the beam depth should be 300 millimeters. Again, what is the next step? The next step is the mesh edge and internal beam. So all this information for edge and internal beam. So we got the depth. Now we look at the bottom reinforcement. So we have two options, mesh or bar alternative. So if we look at here, for the site A flat frame, the depth is 300 millimeter. The mesh can be 3 LTM, LATM. So if we look at this three, so it can be 3 L8TM. So all of them would be this reinforcement. What is the meaning of 3L8TM? Do you know? So we will for the, can you still see my screen? Why are you doing this? Okay, so this is the details we got up to now. If this is the edge beam, so we have D equal to 300 millimeters. The reinforcement here are 3 LHTM. 3 LHTM means the first TM means trench mesh. So first of all, TM means trench mesh, which is made to be used. So this is like a ready rail from the providers, and it is made to be used for specifically in residential footing trenches. So this is the first uh, part of it. Another information we need to know is LM. So L. The second is L. L means low ductility. Eight means 8 millimeter, the assigned diameter. Okay, and three means 3 longitudinal wires based at 100 millimeter from center to center. Okay, do you have any problem with that? And if you are searching for trench mesh, it is made of D500L, which means deformed. The steel should be deformed, and the grade is 500, and L is class L or low ductility. Okay. If we explain that on the diagram or the cross section, so we have these are the three wires, and these are the 8 millimeter about 8 millimeter diameter, and this is repeated each distance. So this is how the trench, how we can interpret the requirement of the standard, which is 3L8TM for the HB or the internal beam. So the internal beam and H beam are similar, 3L8TM. There is no top bar reinforcement in this type of beam, and the max beam spacing is not defined, so it's up to you. You don't have a maximum, so you can use any, but also reasonably can be 5 or 4 meters. I mean, the standard itself doesn't recommend a maximum. So now we know the reinforcement for the HB. We still need to know the reinforcement of the slab itself or the raft itself. So if we look at this part of the standard here, so note, for slab reinforcement for all sides classes shall be the following. If the slab length less than 18 meters, so let's say we have this example, so the mesh will be SL72. So for example, if we have a slab length of less than 18 meters, so this reinforcement is SL72 for all sides. What is meant by SL72? If you have any idea about that? So the slab mesh is SL72. So this is the mesh in plan. We have ray in two directions or in both directions. We need to know what does this mean to interpret. So SL refers to S for square, so the mesh is square. L for low ductility again. So this means that this is a square. Okay. So this dimension is equal to this dimension, and we have 7 2, 7 and 2. 2 indicates 200 millimeter apertures or spacing. So this means that this value should be 200 and 200 millimeter, and 7 means 7 millimeter is the assigned diameter. Okay, so phi, or the diameter of this reinforcement, and this reinforcement is 7 millimeter. Okay, so this is what is meant by SL72. Again, S for square, L for low ductility, 7 for 7 millimeter diameter, 2 for 200 aperture or spacing. Okay, so this is the interpreting of the reinforcement required for this type of stiffened raft, and that's all for the stiffened raft. And are some other considerations when we are designing based on soil reactivity. Few other considerations that we need to take into account, that the beam should be continuous. So if we are designing a stiffened raft or waffle raft or any type of foundation or footing has beam, so the beam should be continuous, and the beam should be under loading bearing walls. So for example, if we look at this example here, so here is the beam are not continuous. So this means that this is a poor design. I need to move this here. So because I have add slides, so this move down. So because here we have the beam is not continuous, so this is considered as a poor design, and cracks will happen in this area, around that area, because the beam are supporting the raft so that the movement of the soil under the raft doesn't affect much. But here, if we are looking at this example, if we when we extend that, so as you can see, all the beam are continuous, and there is no gap similar to here. So is considered as a good design, and no cracks will happen due to soil movement. Because again, the main problem of the expansive soil that the soil movement underneath the foundation is too high. So this will cause cracks and problem in the structure itself. Okay, now we shift to the second part. Sorry, we shift to another part, which is what is the section, what is the problem or the exclusion of section 3? So section 3 doesn't cover the following problem. So section 3 doesn't cover class E or B site. It might be uh, covered by section 4 or need further information to be uh, studied. So some of them of E or B side are covered by section 4 and some need further information. Building longer, buildings longer than 30 millimeter. So if the building, length of the building more than 30 meter, section 3 doesn't cover it. If the building has 3 or more stories, 3 plus stories, so section 3 also doesn't cover it. Construction with concrete strength of 30 millimeter or greater. So if the concrete strength 32 megapascal or more, so section 3 also doesn't cover it. Okay. So if we have this type of problem, so we cannot study it with section 3. We have to look at another standard, or we need further information to design. Okay, another problem we may face while we are designing the uh, footings, shallow footing, is the tree effect on footing. Tree can suck water from 40 to 500, 400 to 500 millimeter beyond the roots. So if we have this, for example, or this example here, so the roots can suck the water at a distance of 500 millimeter beyond. So this means that the existence the existence of trees will affect the soil or the water content in the soil, and will also affect the soil movement. Okay, so the existence of tree will affect the soil movement and extent of the root, mature tree height. Okay, so the tree height and also the the tree the tree age will affect the how much is water it sucked from the soil, and also depends on the tree species species. So all of that might cause significant significant water suction, which lead to significant water movement of the soil. Okay, we are not going in depth in this topic, but we just know that we have some software, CORD or SLOG, often used to uh, measure how much the soil is dug because of the trees, and it follows the standard, the Australian standard. Okay, and because of that, and also because of the uncertainty about the water suction due to trees, suction or movement of soil due to trees, there is a clause in the footing design report should be added just to inform the landlord or the owner of the building that there is significant tree in the vicinity of the proposed work. We have attempted to account for the effect by designing for greater soil movement than would otherwise occur. However, due to the complex tree root geometry, variable soil moisture extraction by the tree, and the difficulty of predicting future growth, a precise design for the tree effects of the tree is outside current knowledge, and the owner must be aware that although precautions have been taken for the effect of the trees in our design, some distortion must be accepted. So this clause is just to inform the owner or landlord that whatever the efforts that have been done to account for the trees and the water sucked by the trees and soil movement, there is no exact solution or uh, exact account for this effect. So you need to accept any cracks or any damage could happen due to the tree. Okay, and there is a guide to homeowner by CSIRO, which indicates that some minor cracks in masonry walls on reactive soils are unavoidable. So look at this one. There is some cracks here. This cracks happen due to those cracks happen due to the reactive soil movement, which is unavoidable. Small cracks, small cracks up to 1 millimeter are acceptable in most houses. So any house that is constructed close to trees, so it will have some problems in cracks. Okay. There is also a care for clay foundation soil to avoid or minimize the cracks. So the aim of this is to reduce the wetting or drying of foundation soil. So one of the things you need to do to reduce because the expansive soil is very sensitive to wet and dry weather and the water content. So we need to have some uh, precautions to reduce the effect. So the first is to have a proper drainage for the houses and also growing grass. So this may affect the wet and the dry. And another another thing we need to do is keep gardening away from the houses. So garden should be a little bit far so the trees cannot suck water underneath the building. Adequate but moderate gardening water. So we need to also control the watering of the soil because of the garden because this also affects the water and soil movement. Tree watering is important during very dry periods or dry period because otherwise the tree root will try to suck the water from far areas. Also, we need to repair the plumbing leaks very as quick as we can and properly install the gutter and down pipe so that the the water or rainwater can be collected or not affecting the soil and the soil movement. And here is another example or class activity for the soil for the design of shallow footing based on the soil reactivity. So in this example, I will solve this for you. So we have to classify the site, select the appropriate dimension and the reinforcement for a stiffened raft design. This example is very close to what is required in the assessment. So it is very useful one for you. So for the site, if we have YS, this is given as 55 millimeter. The site is in a semi-arid area of Australia. The footing area is 17 by 15 meter. The superstructure is a clad frame. So we need to find out the site classification, beam depth, the top reinforcement, bottom reinforcement, max beam spacing, and slab reinforcement. Okay, so first of all, we need to find site classification, and with the superstructure as clad frame, we go to the table with all this info with this two information. So we need to know one, two information. Go to the table to find one, two, three, four, five information. So go to table in AS 2870 2011. So let's see how to start with this one. So classify the site and select appropriate dimension and reinforcement details for a given draft. Y is equal to 55, semi-arid, and this is the area of the building and clad frame. So step number one is site classification. So we look at the characteristic surface movement YS. How much YS? YS in this range between 40 and 60. So this will give us that this site is H1. Okay. So our site classification is H1 and our building is clad frame. So clad frame and H1 site and our footing is different raft. So this is what we need to know, and we'll go to next step now. And also another information we know, because it is semi-arid, so is class H1D, which is semi-arid, so clad frame. The beam depth is 400. The bottom reinforcement is 3L11 TM, alternatively 3N12, and the top reinforcement 1N12, and the maximum spacing between them is 4 meters. Okay, so if we add this information here, so we have, if this is our raft, we have to draw a proper sketch for the different raft, for example, something like that. So we have the top raft, so the raft, the slab itself is has array of, if you remember from the previous example, SL 72 because the length of the building less than 18 meters, and this is the edge beam and internal beam. The depth should be 400, so D equal to 400. The width of the beam for any raft is 300 for any uh, different raft. The maximum spacing between beam is 4 meters. The reinforcement here is 3 L 11 TM, 3 L 11 TM, and we have a top reinforcement. If we go back to the example here, a top reinforcement needs to be added 1 in 12. 1 in 12 means we have to add one more bar here. Size, the diameter is 12 millimeters. Okay, so this is the final sketch of the raft. Do you have any question, guys, for that? Diane or and Geneva? No other question? Okay, here is some construction photos from lead construction. So these are construction of bed footing. So you need to dig the footing size and the depth to place the footing. So for example, this B, this L, and this is D. And you need to add the reinforcement, then place the concrete. So this become a bed footing. And here is your column. So this is an example of bed footing. And here is an example of a strip footing. You also need to dig, add the reinforcement, and then place your concrete. And this is an example of a raft footing. Actually, it is an example of waffle raft, similar to what we were discussing earlier. So we have this trenches. These trenches are made for the beams. Then you add a rail in the beams, and then this is the slab mesh. Then you place your concrete. So you have a waffle raft. Okay, and that's it for the shallow footing, and the next topic will be deep footing. Actually, because the time is now very less, so I will record the another part of the deep footing because it is very short one, and we don't have any like calculation in this part, so I will record it and upload it to the course website. But before we leave, I want to just open the course website with you. So can you see the course website? And we have the assessment. So if we look at the assessment, we have the substructure assignment or assessment. And this is our assignment. So we have the total mark of this is 100 mark and it's equal to 15% of the total grade. So you need to be careful with that. And here is first question. You can do it now after we finalize the self-putting design. And here is a waffle raft. So a close example to what we have done, but it's a waffle raft, not a stiffened raft. And then we have question number two, some like text question or research question. So you have to do that. I think you can solve most of the assignments now, so you can work on it. And let me know if you need any help with that. Okay. So it is very easy and straightforward one. Just let me know if you have any problem with that. Okay. Any question, guys, for now? Okay, guys. Thank you, Dylan, and thank you, Yinuka, to attend today. And I will upload this recording to the website, and I will also add another recording if you can have a look at it. Thanks, and enjoy the rest of your day. See you. Bye.